So in this next example, we're going to come back to the cycloid curve. And here we're going to use the equations of the cycloid, x equals r theta minus sine theta, y equals r 1 minus cosine theta, to find the tangent to the cycloid at the point where theta is pi over 3. So starting with computing dy over dx, which will do y prime over x prime. Here taking y prime with respect to theta, x prime with respect to theta. So let's see, r 1 minus cosine theta, when I differentiate with respect to theta, I get r sine theta. When I differentiate x equals r theta minus sine theta with respect to theta, I have r times 1 minus cosine theta. And now noticing that I can cancel out the r's here. And now we can evaluate at theta equals pi over 3 now. So we have sine pi over 3 over 1 minus cosine of pi over 3. So that would give me sine of pi over 3, which is radical 3 over 2, over 1 minus cosine of pi over 3, which is 1/2. So we have radical 3 over 2 divided by 1/2, which is just square root of 3. And if we're looking for the Cartesian equation of the line, so this is just giving us the slope, we can plug pi over 3 into the x and the y equation to get the point that would be on our curve there. So at pi over 3, x would be r pi over 3 minus sine of pi over 3. And then y would be r times 1 minus cosine of pi over 3. Okay. So with a slope of radical 3 and then a point that passes through these x and y coordinates, you can get the Cartesian equation. But here we just want the slope. And now, at what points is the tangent horizontal and when is it vertical? Well, let's think now. When we set dy dx equal to 0, we get the horizontal tangents. So in this case, setting sine theta over 1 minus cosine theta equal to 0. That occurs when sine theta equals to 0, which means that theta is a multiple of pi. So any integer k will give us, pi k will give us all the values where sine of theta is equal to 0. Now the next question is, when is it going to be horizontal? So let's think about now when it's undefined. Well, notice that it'll be undefined when we get 1 minus cosine of theta equals to 0. And in this case, that would be when cosine of theta equals to 1, which means that theta is equal to pi over 2. Means theta is equal to 0, or any multiple of 2 pi. Notice that coincides with some of these values where we also have horizontal tangents. So notice that sine of 0 is also equal to sine of theta is going to equal to 0 at some points where cosine of theta is equal to 1. So we have to think now, at which points is it going to be vertical and which points is it going to be horizontal? And it helps to visualize the graph here. We know that the cycloid curve looks like this, where as it goes through one complete rotation, it's going to go from 0 to 2 pi with one complete rotation. And then pi here in the middle would be where it reaches the peak. So we could see in actuality, it's going to have horizontal tangents when theta equals pi, or when theta equals 3 pi. But when it's 0, 2 pi, 4 pi, all the even powers are even multiples of pi, it's going to have a vertical tangent. So we see that it's going to have a horizontal tangent at theta equals 2k plus 1 pi, and it'll have a vertical tangent when theta is 2k pi. So that guarantees here these are odd multiples of pi and these are even multiples of pi, because the even ones are where it's going to have a vertical tangent. In the next segment, we're going to think about how to find the area given by a parametric curve. So let's think for a moment here. If I want to find the area under the graph of a function y equals f of x from a to b, we know the area is just going to be the integral from a to b of f of x, which is really just y dx. So if we're given a parametric curve, suppose this is a parametric curve where the xy coordinate are given by f of t, g of t, then the y coordinate is given by g, and the dx, the derivative of the x coordinate, is given by f prime of t dt. Okay, so you see here in the formula this gt is really y and the f prime of t dt is really dx. And notice here these are now integrating from the parameter t equals alpha to t equals beta. So here the points a and b are given by f of alpha and f of beta. So let's look at the cycloid example again. We want to find the area under one arch of the cycloid. So that's one arch would be going from 0 to 2 pi, would be one full arch. So the area here would be the integral from 0 to 2 pi. Our y equation was r times 1 minus cosine theta times the derivative of the x equation. So this is x, so dx would be r times 1 minus cosine theta d theta. Okay, so you see this is what we're inserting here for dx. And this is what we're inserting here for dy, or for y. Okay, so this is going to be integral from 0 to 2 pi r squared 1 minus cosine theta squared. We can FOIL out the expression 1 minus cosine theta. So it'll be 1 minus 2 cosine theta plus cosine squared. And actually, before we integrate, let's use our power reducing formula now to rewrite cosine squared as 1/2 1 plus cosine 2 theta. And then before I integrate here, I'm going to combine my constant terms 1 plus 1/2, so we get 3/2 minus 2 cosine theta plus 1/2 cosine 2 theta. So finally integrating now, we get 3/2 theta minus 2 sine theta plus 1/2 sine 2 theta over 2. And then evaluating from 0 to 2 pi. So I noticed that here sine of 2 pi, sine of 2 times 2 pi, those are both 0. So we're just left with r squared times 3/2 times 2 pi, which gives me 3 pi r squared. Okay, so there's the area inside one arch of our cycloid curve.